Hello friends, today I will be talking through some of the applications of the knowledge that we have been learning likely in the last few videos that we've watched about charged particles in magnetic fields. We are going to start this video by going over some brief review of the principles, starting with looking at calculations of the magnitude of magnetic force experienced. We will then be looking at the movement of a particle within a uniform field, how it causes circular motion, and how that applies to other applications that have been developed and observed. Specifically with the mass spectrometer, the circular motion is very important for us to be able to predict accurately and consistently. And then we will be putting all of this knowledge together to try to create a simple explanation of how the Aurora Borealis is created by the interactions of magnetism and particles from the sun and our atmosphere. We are going to start with a very brief review about how to calculate magnetic force. Likely in the last few videos or lectures you've talked about this, and so we don't need to go into too much detail. As you know, this is the formula that we use to calculate the magnitude of magnetic force, with the force being F over here, and then the charge of a particle that we're interested in, the velocity it's moving at, the strength of the magnetic field that the particle is moving through, and critically, what we are going to be looking at is this right here. The angle between the magnetic field and the velocity component of this particle. Now, one of the things that I want to really quickly review with this is to talk about two different scenarios. So in this case, we have a magnetic field that is pointing to our right, and we're going to create a second one right below it here. These are two magnetic fields. Now, if you have a particle that moves this way through the field, that is a 90-degree angle between the two of these. And recall from your sinusoidal curve that at a 90-degree angle, we are at our maximum, meaning that sine theta of 90 is 1. And so at this point, we are going to be experiencing the most magnetic force that a particle can experience moving through a field. However, if we were to have our velocity component be parallel, either in the same direction or in the opposite direction of the magnetic field, because sine theta would be at these 2 points of our sinusoidal curve, we would be experiencing no force. Now, this is going to be important in a couple minutes as we talk about the Aurora Borealis, but keep this in mind. We will now talk about the predicted movement of a particle in a uniform magnetic field. This is important for us to understand in order to develop effective applications, because if a particle will always behave in the same way if you are able to make these things constant, then we can learn a lot about that particle. Now, for this example, if you were to do your right-hand rule, point your thumb in the direction of this V here, point your pointer finger in, then you would notice that the force seems to be going out this way, but remember that this right here is an electron, so we will be pointing in the opposite direction. I just mentioned that in case you are still a little bit rusty on the right-hand rule and you want to be practicing it. Now, this is a case where we have our velocity moving in one way, and our force, our magnetic force, will always be pointing in towards the center. So that means that at this next moment, if we were to look at this, the velocity will have changed to go in this direction, but the magnetic force will still be pointing towards the center. this will be continuing. Remember the example of centripetal force. So you will continually be having movement in a circle around like this, with the force continually pointing in towards the center, and at any moment that force is causing the direction of your movement of your particle to change. In this example, the field is doing no work on this particle. It can just continually go around and around in this circle forever. And it is important, as we start to think about the Aurora Borealis, it's important to remember that in this case, our movement vector is only in a single direction. We're only calling it this black line. This is one dimension of our vector. With the Aurora Borealis, there will be multiple vectors, but the magnetic force will only be acting on one of those. Okay, we are going to now talk about mass spectrometry. We just talked about movement in a uniform magnetic field, and now we're going to talk about why do we care that we would know how a particle behaves in a uniform magnetic field. Well, recall that formula from the previous page. We have R equals mv over qb. So let's say that we have a particle that we want to know what is the mass of this particle. What do you think we could do? Well, what some very smart people realized is that if you kept everything here constant, if you kept the velocity that the particle was traveling into the field at, if you had the same charge of the particle going into the field, and if the magnetic strength of the field was kept constant, then you could rearrange this formula. We would have RQB over V equals M. This tells us exactly what the mass of our particle would be. Because as it goes in, if the particle is more massive, if the particle weighs more, then as it goes into this field, it's going to take longer to turn. All right? The radius is going to increase as the mass increases. If the mass was smaller, then it would be able to turn more quickly, which is why you're seeing here is a 44 and here's a 46. And that's why we care about being able to tell what the movement of a magnetic of a charge in a magnetic field is going to be. We have all kinds of applications just like this. So we just looked at the mass spectrometer, which is a manufactured instrument designed around the magnetic concepts that we're discussing, and we're now going to look at a very significant example of these concepts within nature. As many of you will know, the Earth has an iron core that is solid in the middle and has a magma shell. And as the Earth rotates, the movement of this magma shell of iron induces a magnetic field around the entirety of the globe. And this field will run from the magnetic North Pole at our South Pole to the magnetic South Pole at our North Pole. And this means that we have magnetic field lines that come out from the globe like this. These field lines are very important because everything out there in space, including our sun, is very dangerous and is basically trying to kill us. So the sun is emitting high energy particles in the form of radiation, and those particles come in from the sun, and they are blocked by this magnetic field that is surrounding the entirety of the Earth. So as these particles are blocked, they get picked up in this magnetic field. And we had spoken earlier about if a particle comes in and crosses the field like this, then there's going to be a large amount of magnetic energy or magnetic force that the particle experiences, and it will move it. But what happens if the particle comes in at a parallel direction? Well, because of the convergence of the magnetic field lines, even if the particle were to enter the magnetic field at an angle where it was parallel, as the magnetic field lines converge, it eventually is not going to be parallel. And as soon as it is not parallel, you begin to see this circular motion exhibited here. And this circular motion, along with the natural momentum of the particle as it comes from the sun, means that these radioactive particles, these high energy particles, are going to be deposited at the end of that magnetic stream. In other words, they're going to be deposited at the poles, but as they travel through here, through this magnetic field, they're increasingly gaining momentum, and that increase in speed excites particles that are around them in the atmosphere, nitrogen and oxygen. And in order for that energy to be released, photons are emitted. And these photons are what we call the auroras. At the North Pole, the Aurora Borealis, and at the South Pole, the Aurora Australis. And we can understand these amazing phenomena just by applying these principles that we've discussed in the last 10 minutes. In addition to some principles that you'll learn about with electron excitability and photon emission. But these basic principles help us to understand this amazing phenomenon that we see at the poles of our Earth.